All right. Okay, so as mentioned, I'm Joe Izraelevitz. I'm a postdoc here at UCSD, and actually starting August, I'll be a professor at CU Boulder. I'm here to talk about our empirical guide to scalable persistent memory. This is work that was done really with the whole NVSL group here at UCSD and represents a lot of experiments, and our idea was to try to extract some practical guidelines for using the new Optane DIMMs, and so I'm here to share that with you. So the motivation for this work is that Optane DIMMs are finally here. That's cool. And so that's all. Sit back down. And I'm here to convince you that it's not just slow, dense DRAM, and that it's actually important to think of it not as slow, dense DRAM, but as another hardware device that has intricate internals that you need to be aware of when you're writing performing code. So it has slower media, which leads to a more complex architecture, which leads to second-order performance anomalies, which means that it's fundamentally different when you're writing software for it. And I'd like to convince you of this point and then show you why this is true. So the outline for this talk, I'm going to go a little bit over the background of where Optane DIMMs fit into the machine and what they look like on the inside. We're going to cover a little bit of what the basic performance characteristics are of these devices. I want to extract some best practices that I can share with you, and you can hopefully take back with you back to the companies you came from, or you can argue with me about them. It's also valid. And then we'll conclude. So the first is some background about where Optane DIMMs fit in the machine. So here we have a 3-core socket. Okay, fine. So and each core has a private L1, L2 cache and an shared L3 cache. And then we have the memory controllers. And attached to these memory controllers on most of the machines out there is a bunch of DRAM DIMMs. Now, if you want to go out and buy some new fancy Optane, well, what are you going to do? You're going to attach it to these same memory controllers, and they're going to share a channel with DRAM. So you're going to have at most 3 channels with each support 2 DIMMs. And your options, you can either use Optane as in app direct mode, which allows you to directly access the device as a persistent memory, or you can use it in memory mode, in which case the hardware is going to manage the adjacent DRAM DIMMs with Optane. They're going to function as another level of the cache, and the hardware and operating system are basically just going to see a large pool of DRAM, and it's not going to know anything about the fact that there's Optane attached. This talk is going to entirely talk about the right-hand side of this figure. Okay, so that's where Optane fits into the machine. I want to talk a little bit about the Optane internals, because the Optane internals really determine some really interesting performance effects. So here we have an Optane DIMM. Ta-da. The Optane DIMM attaches to the CPU through, again, the IMC. And so writes from the CPU are going to hit the write pending queue, which sits in the IMC, which is then going to issue the writes down to the Optane DIMM. The writes are going to be received by what we call the Optane controller. It's just the controller on the device. And this controller is then going to issue writes back to the actual Optane media. Now, what's really interesting, which has been alluded to earlier in this conference, is that this communication occurs over a 256-byte block, and this is for current generation of Optane, and apparently this might change. But right now, it's true and it's important, and we're going to talk about it periodically. But because the IMC and the rest of the cache hierarchy work at the granularity of cache line, 64 bytes, that means that the Optane controller needs to have some sort of buffer that's adjacent to or attached to the controller, which allows you to merge adjacent writes in order to build up this 256-byte block and write it back to Optane media. Now, one other thing that's going on inside of this is we need some method of doing address translation. So there's a physical address, but there's also a device address. The address indirection table, or AIT, is the way that we do that, and this is cached in the creatively named AIT cache. Okay, So all of this is kind of what's going on in the internals of this device. I want to mention one other thing, which is the ADR domain, the asynchronous DRAM refresh domain. This is the point at which writes become persistent. And they become persistent actually once they reach the memory controller, as opposed to once they reach the DIMM. And this is because we've got enough stand-up power in the machine that we can empty the write pending queue into the Optane controller, and we can empty the Optane controller and its buffer into Optane media. Okay, so that was a lot of things inside of a device, but I want to mention one other thing as part of this background that actually has serious performance implications. So Optane is interleaved across the various DIMMs, or can be interleaved, at 4K granularity. So if you have these 6 Optane DIMMs, your physical address space can be laid out in 4K blocks where you go 1, 4, 2, 5, 3, 6, and then back around. So for every 24K stripe, you're going to touch all 6 of these Optane DIMMs. Now this is an option. You can either interleave your DIMMs or you cannot, but if you do interleave, this is what you're going to get. As far as we know, there aren't other options for how you interleave Optane. Okay, so that's a lot of information about how Optane fits in the machine, what it looks like on the inside. So now how does Optane DC perform? And the background for this, I want to briefly touch on our approach. So our idea was basically to just suck in a lot of data. So we did a bunch of micro benchmarks that just swept across the state space. We looked at access patterns, if they're random or sequential, different types of access operations, reads, writes, different access sizes, stride sizes, power budget, NUMA configuration, whether or not we're doing address space interleaving. We ended up running 10, and then once we discovered any interesting performance anomalies, then we ran some targeted experiments trying to figure out what's going on. Total, we ran about 10,000 different experiments trying to understand this device. So I hope, even at this point, you believe that it's perhaps not just slow, dense DRAM. This is our test platform. I don't think there's a lot to say about it. I guess if there's any questions, just briefly, we had a total of 384 gigabytes of DRAM across our 2 sockets, each with 6 channels, and 3 terabytes of Optane across 2 sockets with 6 channels. And this is the new Intel Cascade Lake. So we had 24 cores, a total of 48 cores in 2 sockets. Okay, so very briefly, what is the latency? So the latency that we saw was 2x to 3x slower than DRAM. And where does the 2x to 3x? Well, this has to do with if you access it either sequentially or randomly. If you access it randomly, you're going to get slower performance. That's the 3x. Sequential is the 2x. What's interesting about the write latency is that it's basically the same as DRAM, which was kind of surprising, but if you think about it, it makes sense because writes only reach the ADR domain, so they're going to reach the same point, which is the memory controller, before they're acknowledged, so it's going to have the same latency. Okay, for bandwidth, what we saw can be summarized as approximately scalable reads and not really scalable writes. So on the left, we have DRAM. This is read bandwidth, writes using the nontemporal store instruction, and writes using store plus CLWB at the bottom. And this is with DRAM. When we when we interleave the DIMMs, what we see is we see basically scalable reads, and writes scale up to 4 to 6 threads. When we don't interleave, we can actually saturate the write bandwidth with like 2 or 3 threads, depending on what instruction we use for write bandwidth. And similarly, for reads, we max out at 4 threads for an individual DIMM. Okay. Now, the next thing is looking at bandwidth versus access size. So if we look at this, what we see for DRAM, it actually doesn't really matter what access size you use when you're looking at bandwidth of DRAM. In contrast, if you have a non-interleaved Optane DIMM, you're going to ramp up to 256 bytes. And this makes a lot of sense if we think about the architecture of the device, namely that the communication between the controller and the media occurs at 256 bytes. So if you have small random writes, you're not going to see as good bandwidth. Okay, and now briefly I'm going to give you a mystery. that I'll allow you to think about for most of the rest of the talk. I'll give you the answer in about 10 minutes. So this is the same chart. We're growing the access size. This is bandwidth, read, write, NT store. And what you see is we very quickly we reach a peak at 256, and then our bandwidth drops to a valley at 4K, and then we gradually ramp back up. And unlike most systems charts, this is really weird because most systems charts you expect to be monotonic. So I'll let you puzzle over that for 10 minutes, and I'll give you the answer later. Okay, so these are the basics of the Optane DIMM, the basic performance characteristics. So what are the practical performance lessons that we should take away from this for programming? And we came up with 4 of them. 1, avoid small random accesses. 2, use non-temporal stores for large writes. 3, limit the number of threads accessing one NVDIMM. And 4, avoid mixed and multi-threaded NUMA accesses. And I'd like to justify this and give you kind of a more detailed story, but maybe this is the executive summary of what you should take away. Okay, so 1, avoid small random accesses. Well, we kind of understand why that's happening. And it really comes down to this 256 byte block. That if you do accesses that are smaller than 256 bytes, they're going to grow to 256 bytes, and you're going to see less bandwidth. Now, exactly how these smaller writes are going to merge into the larger writes, right? This happens within the Optane buffer. And we were able to measure the size of the Optane buffer by looking at write amplification. There are counters within both the memory controller and the Optane DIMM, so we figured out that it's actually about 16K. Look for validation here. So long as your writes stay within 16K, that means they're approximately sequential. You're using the cache effectively, and you're going to see this merging effect up to 256 bytes. And if you don't, you're going to see write amplification. Okay, so avoid small random accesses. You're going to get bad bandwidth if you have random writes that are smaller than 256 bytes. But if your accesses are smaller than 256 bytes, you can still get decent performance if your working set size is smaller than 16K. Okay, so that's the answer. And you get good bandwidth with sequential accesses. Lesson number 2 is use non-temporal stores for large writes. And just briefly, if you don't know what a non-temporal store is, non-temporal stores bypass the cache. They don't pull in a line into the cache, they just go directly to memory. So here's a bunch of ways that you can write to a persistent Optane DIMM. You can use an NT store, which again just goes directly from the CPU up into Optane. Another option that you can use is a store plus the CLWB or a CL write back, which is going to clean the cache line back into Optane. What this is going to do is it's going to pull the line out of Optane into your cache. Secondly, you're going to write to the line, and 3, it's going to be written back. This is the CLWB. So 1 and 2 are the store, and 3 is the CLWB. Your other option is you can just use a store, right? You can just pull it in, do the write, and then sometime later your cache eviction policy is going to decide that we don't need this cache line anymore. It's going to get written back. Okay, so what happens when we use these other 2 options? Well, with a store plus CLWB, we lose bandwidth because we're using part of Optane's limited bandwidth to do this cache line pull, okay? And then if we're using the store, we actually have an additional penalty, which is we lose locality, and we lose our effective write ratio. We experience write amplification. Because we're introducing non-determinism from the cache back into the device, what we see is we're not actually getting the right combining and an efficient use of the buffer on the DIMM, and so we experience a loss of bandwidth. And this is our experiment justifying this. So you can see, actually, if you use NT store, you can get up to 6x performance over a regular store without a CLWB because you're losing the locality within the Optane buffer. Okay, so non-temporal stores bypass the cache, and they avoid a cache line read and maintain locality.
So
yeah.
That previous slide.
Sure.
So that assumes that you're not going to revisit the data in the cache.
Correct.
Okay.
Correct. Yeah.
So you're blowing the cache, so it's not doing any good on that bottom line down there.
Correct. Okay. But you're losing bandwidth. Yeah.
So story, if you revisited it, then the bottom line would be the thing on top, and the NT store would be the thing that's screwing you.
Sure.
You'd never cache.
Sure, sure. Okay. So the next lesson is to limit threads accessing a single NVDIMM, or a single Optane DIMM. And the reason for this, there's actually twofold reasons. So one is contention at the buffer within the device, and the other one is contention at the memory controller. Okay, so how do we see contention at the Optane buffer? Well, if we have more threads, that means that we're trashing our buffer on the device, which leads to access amplification, which leads to lower bandwidth. So once we get to a position where we have enough threads that threads can't effectively use this Optane buffer that resides on the device, then we're going to see a loss in bandwidth. And this happens once we hit, I guess, about 8 threads for writes or 10 threads for reads. Okay, so this is a pretty straightforward story, but I want to share with you a slightly more complex story, which is contention at the memory controller. So the thing is that the memory controllers weren't really designed for Optane, they were designed for DRAM. And so they really aren't designed for slow variable latency accesses. And these short queues that we have on the integrated memory controller end up getting clogged. So an experiment that we ran was to vary the number of threads that are accessing an individual DIMM. And so what we have 6 threads in this entire experiment. And what we vary is the number of threads that are accessing an individual DIMM. So with 6 threads, all 6 threads are accessing one DIMM. And with 3 threads, 3 are accessing one and 3 are accessing another. And then with 1 thread, we're using 6 DIMMs. And what you see is, well, we increase bandwidth up to 256, and then we start seeing this fall off as more threads are accessing an individual DIMM. And what it seems to be happening is we're getting this head of line effect, where because the device is slower than the memory controller is used to or designed for, we experience back pressure from the device to the memory controller back to the CPU, which is going to slow down our access requests. And this story actually answers the mystery that I introduced to you about 10 minutes ago. So memory controller contention is actually largest when the random access size equals the interleave size. So if you think about, so all of our different threads are generating random 4K accesses. And because it's random, sometimes they're going to fall on one memory controller and sometimes on another. And periodically, they're all going to land on one memory controller. And we're going to experience this case where we have 6 threads accessing one DIMM, and we're going to have this bandwidth plummeting. But if we have accesses that are larger than 4K, well, larger than 4K means that they're going to be interleaved across DIMMs, which means that it's never the case where we can have all 6 threads accessing one DIMM. They're going to be using 3 on one or 3 on the other. And so actually our most uniform access is going to be when our access size equals the number of DIMMs times the interleave size. So we actually get an access or a bandwidth peak when we hit 24K and 48K because we're uniformly loading all of our DIMMs, and we're going to see this better performance. Okay, so this is lesson number 3. Limit the number of threads accessing one NVDIMM. This avoids contention at the Optane buffer, which avoids access amplification, and also avoids contention at the IMC. And contention at the IMC means that we're going to have bandwidth loss through uneven NVDIMM load, and we should really try to avoid interleave aligned random accesses, because then you're going to fall right in the bottom of this valley. Okay, so I have one more lesson to share with you, which is this notion to avoid mixed and multi-thread NUMA accesses. And basically the story here is that NUMA effects impact Optane more than DRAM, and it impacts it in kind of a weird way. In that, read and write ratio is much more important. So what we see is if we have a multi-threaded NUMA access, and we have all reads, we're okay. And if we have all writes, well, we're okay. We still see some NUMA effect. But as we introduce writes, we actually see this pit here. Exactly why isn't clear. We believe it's, again, one of these memory controller wasn't designed for this sort of thing, where we see some long latency accesses, and we basically clog up the NUMA pipeline, but this is just a hypothesis. All right. So to conclude, I'd like to hopefully have convinced you that Optane DIMMs aren't just slow, dense DRAM. There is slower media, which leads to a more complex architecture. We get these second-order performance anomalies, and it really is fundamentally different. And we should be aware of these constraints when we're optimizing code for these devices. Maximum performance is tricky. You need to avoid small random accesses, use non-temporal stores for large writes, limit the number of threads accessing one NVDIMM, and avoid mixed and multi-thread NUMA accesses. Now, I want to point out that all of these lessons are for the current generation of Optane DIMMs. I imagine that probably these devices are going to be tuned, and we're going to see probably different parameters in the next generation, as has been alluded to. But hopefully these lessons have been presented in a way that you're aware of kind of the fundamental design constraints of these devices. And I imagine that while the size of the peaks and where they are won't change, they'll probably still exist. So with that, I'll open the floor to questions. Thank you.
So in this one on the right,
Yeah.
it occurs to me that since that's level 3 cache, I think, right?
Sure.
That since it's in level 3 cache, you're a von Neumann.
Okay.
Harvard architecture, first cache,
Mm-hmm.
separate code and data.
Mm-hmm.
So the thing causing this eviction could be an instruction cache.
Sure.
So it's waiting for this 4K block in this clip to be transmitted before the instruction can be actually fetched up.
So this is a different. So this is a different anomaly. This is that kind of the cache eviction policy is not optimized for Optane bandwidth, right? And so
in the regular old cache hierarchy.
yeah. So because the cache eviction policy is not going to pay attention to this 256 byte block, it's going to evict cache lines kind of willy-nilly, and it's probably not going to be in 256 byte increments.
Could the thing causing the eviction be instruction cache?
Could be whatever. Yeah.
Okay. If that's the case, then it's waiting on this eviction, which may take a while.
Conceivably, yes.
The question is, on a busy system, because the eviction
Sure.
is code, right?
Right.
So you have to have a busy enough system that there's back pressure, even affecting your eviction.
Mm-hmm.
So could you, on an instruction fetch, have to wait the right medium speed for that eviction? And the answer is yes.
Yes.
And if that's
any
true,
of course.
And it's a critical instruction for the operating system.
Mm-hmm.
Yeah, you can wait for that. I mean, they're multi-set caches. There's, like I say, there are queues, and these evictions are posted. So you have to get the conditions just right, of course, for that. Just that.
What's wrong with the IMC? Is it not deep enough? Does it need to be multi-queued?
Yeah. So we think it's not deep enough.
It's going to get a headline block.
Yeah. So this does seem to be kind of a tuning problem, in a way that, right? So these things were designed for DRAM, right? So
Predictable latency.
yeah.
Every
And,
write takes the same time.
right. And a different amount of time from what you would see for Optane. So I don't have a hardware solution.
I'm
but
just curious
yeah.
if you figured out what's wrong with it.
So I'm trying to remember, I think we could fit, I don't remember the size that we measured, but it was I think 1K, something like that. I mean, it was pretty easy to fill it. And that seemed to be the likely culprit for that. But again, you grow the queue, and then you've got all these other problems. So, yeah.
Do you look at any kind of change in behavior over the life of the device? Or do you know of anyone has?
So we didn't. The only thing I can say is that we've been running these experiments since September, and I'm not aware of anything that we've noticed. So that's the strongest statement I think I can make with respect to that.
I guess we'll find out in
Yeah.
like 2 years. Burn them. Burn them.
Sorry? What do you mean? We did not check for row hammer. Yeah.
Because I know flash suffers from it.
Yeah.
Apparently DRAM does too. So it's quite possible that it's...
Having been invited into Intel's house, where's the memory? It seemed unwise to try to destroy it.
Or hack.
Yes.
So, yeah, follow up to what Steve just said. If I give you some new piece of machinery, like I give you a tank, you might measure its speed and its gas mileage. You're probably also going to want to test it to destruction, right? You want to find out how to kill it.
Yeah.
So any potentially endurance limited device, I would want to just write the 10-line program that writes to it, and writes to it, and writes to it until it fries. Are you going to try that?
So these were DIMMs graciously provided by Intel Corporation. So
But they tell
yeah.
you how worn out they are. There's a management book, so you can count on them. Doing what you're doing would take a long time. But you could at least count on them and then look to see what they're reporting as their wear out level.
Right.
And maybe extrapolate.
Yeah.
Actually, I'd be able to see it all. Well, no, maybe the parts that gave you earlier than now people.
They just lie.
But they should. So if you're always seeing 0%, then what you talk about it.
That's a pretty good part.
You got a really good chart.
Yeah.
So your recommendations, like the, remembering the order, like the first one and the third one are things that are generally, you go back to your
Sure. Oh. Nah. Yeah, we'll just go like this.
I mean, like the first one is terrible for all storage in the world. So,
Yeah, but it's not true for DRAM.
It's not true for DRAM, that's the point.
Particular device is smaller.
Yeah, particular those small.
Yeah.
That's not true. Like, I mean, if you draw the line for bandwidth versus access size for DRAM, it's essentially flat.
Yeah.
I can get about the same amount, or like, bandwidth.
Yeah, I mean, I can. Yeah, I do.
And that means it's very, that one.
Yeah.
It's very easy for bandwidth versus bandwidth.
You started at 64 bytes.
Yeah.
You can't actually issue a 1-byte access.
Well, you
Right.
can
Kind of
have
cache
a
line.
space, so you can for the application.
And bandwidth would actually be, by that measure, bandwidth would be higher, probably.
No. 1 byte access
Yeah,
is
worse.
widespread. Right? You miss the count.
Yeah.
And then performance sucks.
DRAM is the serial
but
I mean, but
you can't store persistently with DRAM. So I guess I'm comparing this like to the advice you would normally give to a storage, the application trying to.
Sure,
a storage
sure.
device. But the other two.
yeah. I don't know.
See. So yeah, like as good advice for like running your benchmark. But is there anything in you think I mean, do you think an application can practically do to
Yeah, so we thought about this. So actually, this was part of a paper submission. And really, for each of these lessons, what we did was we applied them to more or less Nova and a couple other things where we said, okay, and using this optimization, we were able to get 5% up to, I think, 30% performance improvement. I think the limit the number of threads accessing one NVDIMM was the one where we got the most performance improvement. It really, at the level of like the Nova file system, it actually does make sense to conceivably pin a thread to an individual DIMM or pay attention to this, right? So I'm not sure, it depends on the application and how performance critical the application is, but
What if the system is virtualized? I mean, imagine a cloud provider.
Sure.
Let's just say.
Mhm.
We're going to deploy these things.
Mhm.
How do they configure their machines to provide an SLA? Because if they just put 75 VMs on a 32-core machine,
Mhm.
might otherwise work well. All of a sudden, it drives it into that hole in your thing.
Sure, conceivably.
So it should be
Yeah.
recommended that threads accessing one NVDIMM if they're intermittent.
Right.
And they're almost always early.
Yeah.
So that's an interesting point. It's
Yeah.
a hard one to really honor.
Sure.
If your application has a workload that involves small random access, you can't avoid it.
No, I mean, it's right. True, true.
Update one indirect pointer because it just allocated a block.
Mhm. So we did think about this, and we were thinking, well, maybe we could say, well, it's really like 16K, right? Like, how clever can we be with this 16K in order to avoid kind of falling into this pit, right? Can we fit enough performance critical code to just use that area such that we can consolidate all of our small random writes into that? And like, obviously for a lot of workloads, it's impossible, but for some it might be. So.
But you could also architect your system, right? Like
Yeah.
we architect B trees because there's 4 kilobyte disk accesses. And so now the answer is, well, you have 16 kilobytes, so you should architect your data structures to have those properties. And adapting existing code does can be very hard in some cases. But if you're starting from scratch, then these are sort of the principles that you should keep in mind.
The Tom's point, that's only true of bare metal, right? It's going to be a virtualized thing.
Yeah, and if you're gonna be, you've got an application-specific solution at that point, which, trust me, you sell totally different.
I mean, it's no more application specific than,
But I've got a B tree that's optimized to this type of RAM, and now I've got to deploy a system with this type of RAM to deploy this application with the B tree. It's like, they get this deadly embrace on one another.
I don't see, I mean, this is one of the questions that came to mind when we were talking earlier about virtualization, is and when you said, oh, you still need to be able to handle the fact when mmap doesn't work and you got to go back and do upstream. If you have to have the code and the complexity and the reasoning and everything for upstream, and you're going to run this virtualized environment where you've got all these layers in between, and you've got to go and deal with all this other, many layers of garbage, like, that just seems like a bad idea for persistent memory, right? I mean, you need to have something that's much closer to bare metal. Because otherwise, I mean, the programming model is nice, but it in itself is not a reason to change anything.
But not every system comes with Optane DIMMs in. Right?
Sure, sure.
With a platinum
But I mean, there's software that's designed for certain devices. Yeah.
Yeah, my question is, did you notice that when you were doing write, I think I know what's going on with the write and read, why it slows down.
Mm-hmm.
If you're doing a whole bunch of writes and reads, it goes like this.
Yeah.
I think it's because the Optane's controller, the memory controller, is getting overloaded. I mean, the thing is, you said you can write as fast, and the write time doesn't matter.
Mm-hmm.
But that is only true if you don't get back to it before the actual write
Sure.
has been done to the device. And if you're pounding on it, you can actually send it data faster than it can write.
It's pipeline,
Yeah.
Right, yeah.
Now, you can definitely do that if you have very highly tuned
Sure.
code.
So have you conducted or do you plan to conduct any tests of the persistence property itself? In other words, try to find out if under PowerCall, all the data that should be safe is. Early generation SSDs,
Yeah.
they just didn't work.
Yeah, I mean, we would love to run those experiments. These were remote machines, so it's hard to power cycle them in a. Oh well, yeah.
So we have one of my students is doing an experiment where we write lots of data and we don't do the flushes and then we kill the machine to empirically measure what actually doesn't make it.
Well, a more interesting thing is, another complementary
Mm-hmm.
exercise is to follow all the rules and, just reason about what ought to be present upon recovery and see if it actually is. Because a colleague of ours, a former colleague of ours, wrote a paper in 2013 doing that experiment with SSDs, and I think 13 out of 15 simply don't have the data that they're supposed to have when you turn the power back on.
Is that why you know where you're
One thing that we noticed with this NT stores for large
Mhm.
writes, in memory mode, it seemed as if we wanted to do the opposite, that we got really bad performance with NT stores for the memory mode.
I think another important thing is to flip it around and go, well, based on all this data, what should designers of persistent memory DIMMs do to make it easier for applications?
Yeah.
But what do we do at the application level to accommodate for this crappy hardware? It's probably going to change. So if there's anyone developing persistent memory DIMMs in the room, we want our code. Seems like this is pretty good feedback.
They want the phony.
We want coding. I want zero latency, zero error correction required, total randomized. You could make that product company.
Appropriate infinite capacity.
I think it's interesting because there's a trade-off here on cost as well, right?
Sure.
256 was chosen to get a certain amount of endurance for a certain bit error rate on the raw medium, and that's cost, because you could say, I'll go with crappier medium, and the error rate's higher, but I'll accommodate with error correction for a larger block size, and I get cheaper Optane.
Sure.
And that's a decision that the market and Intel and others can make as they design this stuff. But it'll affect applications even more, because now it's not 256 bytes, it's 4K.
One other dimension of application limits I'm looking at is the ratio.
Mm-hmm.
So you did 1:8, but you could also do in terms of DRAM versus Optane
Mm-hmm.
sizes. You could do 1:4 or 1:2, etc.
Sure. We didn't really look at that. Again, almost all of our experiments were in app direct mode, so we're just looking basic. Sure. No, I.
Remember to do a postal application supported on a CS server using Optane, then maybe I don't go to the extreme and I stay.
Sure. No, I think there's an equivalent talk you could give on memory mode. Yeah.
The fact that you had to discover the 16K buffer
Yeah.
size, I mean, I don't think it was easy.
No. Actually, I wasn't quite sure how many of those things there were. You know, the hardware guys just put as many as they could fit in there. And I never actually got the number from them. So that's actually kind of.
Yeah, I'm not sure it is 16K, but the fact that you found it is interesting. But should applications, should that be advertised somewhere? Like, and if it is,
Yeah.
Reynolds and Allocator are going to code.
Yeah. Yeah. I mean,
We're already asking applications to get pretty complex. That piece of information would take more than a paragraph to describe to let alone know what to do with it.
yeah.
Maybe to a run.
Yeah. So I could imagine a runtime that would want to know the size of the buffer, the size of the block, and the size of the interleaf size, right? So.
For example, we could make it go discover that and then do something
Yeah.
different. I'm not sure what.
Yeah, when you said like, oh, Nova could get submitted, that makes a lot of sense because the kernel can figure it out
Right.
and do stuff, and the application has no chance.
Yeah, that's more practical.
Other questions? Okay. Yeah. I'm not aware of any that would change.
What was your reading cover? Because I saw you using 413, I kind of died inside.
Sorry?
What was generating the traffic? I saw the kernel you were using was.
Was a custom piece of software that runs in the kernel.
Okay.
So,
You
yeah.
use mapping directly.
Yeah.
The kernel really didn't.
Yeah.